Hi guys, I'm Jeff, and I specialize in teaching both IB Economics Higher Level and IB Math Standard Level. Currently, I'm a second year student in UC Berkeley studying both applied math and computer science. I've always had a lifelong passion for mathematics. I can see math in everything in all realms of life, and I feel like the problem-solving skill set that you get from math can be applied and to a lot of other subjects and get you further in a lot of other subjects, whether it be econ or bio or even physics. And as for economics, it was my favorite subject in high school, and I've always had a passion for it as well. Um, I've actually had tutoring experience in college before, so I was a group study session leader for computer science and also applied math. So for today's demo lesson, I'm going to be teaching one of the integration techniques in math called u-substitution. Hi guys, so today we're going to be talking about one of the integration techniques called u-substitution. Um, and basically the concept of u-substitution is when you encounter an integral where there are two different functions of the variable you're trying to integrate with respect to. And that can sound pretty confusing, but if you look at the example I give here, um, the integral of ln x over x dx, here you're trying to integrate with respect to the variable x. So right off the bat, you can recognize that the derivative of ln x is actually 1 over x, which happens to be a part of the integral that you're trying to integrate. So that's all u-substitution is. You're trying to look for one part of the integral whose derivative is the other part, and that part is your u. So in this case, your one part of the integral, ln x, the derivative of ln x is 1 over x. So your u in this case should be ln x. And it probably sounds pretty confusing right now, but we'll take a look at some examples to better clarify this concept. So here's example one. It's literally the example that I just showed you. And here, the integral of ln x over x dx, we can see that we're trying to set u equal to ln x, which is what we do here. So u equals ln x. And after this, you can, if you find the derivative of ln x, like we said before, it's 1 over x. So du over dx equals 1 over x. And here you can see that you can rearrange this entire equation right here to make it dx equals x du. So all you're doing here is just multiplying dx on both sides and multiplying x on both sides to get dx equals x du. And we can see here that the dx here is the same as dx here. So you can actually sub in the x du back into this equation and sub the u back into this integral to get u over x multiplied by x du, since we substituted u for ln x, and here x du for dx. And here you can see that we can actually cancel out the two x's in the integral, and therefore get the integral u du, which is something that we can actually integrate pretty easily. So the integral of u du is actually just half u squared plus c. That's just basic integration where you take the exponent of u, you add 1 to it, and then you divide that exponent. You divide u by that exponent. So here's the final answer of this integral. And oh, sorry, that's not the final answer actually. Sorry. Yeah, I still have to actually substitute the u back into your function here. So we set u to be ln x. So actually, the final answer here should be half ln x squared plus c. Here's another example. It's the integral of t times e to the power of 2t squared plus 3. This can be a daunting integral for anyone when they first see it. But if you take a closer look, you can actually see that the part of the exponent of the e of Euler's number is 2t squared plus 3. And the derivative of that is actually 4t. And and since t is already part of your integral here, you should actually set u to be 2t squared plus 3, because you can cancel out the t afterwards, and we'll see that in action later on. So here u equals 2t squared plus 3, and same as before, you find the derivative of that to be du over dt equals 4t. And you can actually rearrange that like we did before to isolate dt to be du over 4t. And here you can sub that dt back into your original integral to get t multiplied by e to the power of u, since we set u to be the exponent of e, and then multiply that by du over 4t. And here you can see that we can pretty easily cancel out the t here and the t here, since it's dividing by t. And that gives you a quarter of the integral e to the power of u du, since we have 1/4 right here. And again, this is a pretty easy integral to evaluate now, since we're integrating with respect to u. And the integral of e to the power of u is just eu, e to the power of u. So here, and then you multiply that by a quarter, and you add the integration constant c. So the final answer, after you sub the u back in here, is a quarter e to the power of 2t squared plus 3 plus c. And here I should actually point out that you have to be careful when you're integrating definite integrals, which means that you're integrating over a bound. Since before we actually integrated indefinite integrals where there are no bounds, it doesn't really matter that you substituted the u for your x function. But when you're integrating over a definite bound, the bounds for x don't apply to u. What that means, I'll point out with an example later on. But here you basically have two options. When performing integration over with definite integrals, you can either rewrite the bounds so they apply to u by substituting the x bounds back into the u function, or two, evaluate the integral indefinitely first, then substitute the u function back in like we did before. So what those two mean, I'll talk about right here. So let's say we're trying to integrate this definite integral from 0 to 2 of x over 1 plus 2x squared, all squared, dx. So here, the option number 1 is to rewrite the bounds. But no matter which option you choose, you actually start out the same way. You try to find u first, so you're trying to find a part of the integral of the integrand, so the function that you're integrating, that whose derivative is one part of whose derivative is another part of the same integrand. So in this case, if you set u to be 1 plus 2x squared, you can immediately see that if you differentiate this, then you get du over dx equals 4x. And since you get that, you can actually later on cancel out the x's. And here, you can rearrange like we did before to isolate dx to get du over 4x equals dx. And you can actually substitute this back in right now to this, but I'd like to point out here that this right here is actually incorrect, because the bounds 0 to 2 actually only apply to x. And since now you're trying to integrate with respect to u, the bounds don't apply now. So the option here is to rewrite the bounds. So to rewrite the bounds, you have to sub x equals 0 into your u function, which is here. So substitute x equals 0 for the bottom bound to get u equals 1. and then substitute x equals 2, so your top bound, to get u equals 9. And then, therefore, you can actually rewrite this integral to be 1 to 9 of x over u squared times du over 4x. And then you can obviously cancel out the x's here to get 1/4 of the integral of 1 over u squared from 1 to 9 du. And this is a pretty easy integral to evaluate once again, because this is technically just this part of the integral is just u to the power of -2. And that, when you integrate that, you get negative u to the power of -1. And then with the bounds 1 to 9. And then you just evaluate it like you would for any other definite integral. And you get 1/4 multiplied by -1/9 plus 1. And then you just do some basic algebra, and you get the final answer to be 2/9. The option 2 here is to actually integrate indefinitely first. So this is actually my preferred method because it saves you the step of rewriting the bounds. And essentially, this is the same stuff as we've done for examples 1 and 2 for the indefinite integrals without the bounds. You do the exact same thing as you would with option 1. You find a u, you differentiate the u, and then you rewrite it so you can isolate dx and substitute it back into your original integral. And here in this integral, instead of writing the bounds to be 0 to 2, or even rewriting the bounds to be 1 to 9, just evaluate it indefinitely first, like you would for examples 1 and 2. And you continue going to get, you cancel out the x's here, and then you get 1/4 of the integral of 1 over u squared du. And then here, you would just evaluate it to be 1/4 of negative u to the power of -1 plus c. And then, since it is after all a definite integral, you should substitute the u function back into the result that you got here to get 1/4 of -1 plus 2x squared to the power of -1 from 0 to 2. So once you do that, this is anything to the power of -1 is obviously just 1 over that thing. So 1 over 1 plus 2x squared. And then you would just evaluate this like you would for any other definite integral from 0 to 2. You plug the 2 back in, and you plug the 0 back in to get 1/4 of -1/9 plus 1, which is the same thing as we had before, which equals 2 over 9. So that's it for today. I hope you actually learned something useful. I feel like u-substitution is very useful for when you encounter integrals of two functions of the same variable where one function is the derivative of another. So now when you see those, you don't have to fear. And thank you, and I hope to see you guys and work with you guys again soon.